communications group to to hook us up. So they still have to terminate that fiber and give us a new modem that operates on the fiber, and then we'll be hooked up to a broadband connection. So we're waiting for them to tell us when they can do that.
Hey,
Uh,
Bill.
yeah, go ahead.
Gosh, I actually got a hold of ES Technologies today as I was busy, and I spoke to Clint, who's the operations manager for them,
Yep.
and he promised me that we will have fiber internet before the end of next week.
Oh wow. Well,
So
that'd be great. Yeah.
they'll Kara, who's the lady on the front desk there, she said she'll call me ahead of time, give us a little bit of lead time, so she'll know, or we'll know when they're going to be on site, and they will be helping us hook all the fiber up.
Okay. I wanted to mention the other thing they did for us was we were trying to figure out how we were going to get a connection made to the bunker and out to the gate. And they went ahead and pulled in an additional fiber. They have a unique machine called a vibratory plow. I call it a mini sneaker or a sneaker. And they fed two fiber cables into that machine, and it just drags the fiber in on a shank, on a vibratory shank that goes in the ground. And they pulled all the fiber in one day, and also pulled in additional strand for us. So now we have a fiber loop going into the bunker and back out and out to the gate, and that's all connected to the main control room in the new building. And so we'll have to get that terminated too and hooked up to our fiber switch. We'll have another fiber switch in the bunker and a sub switch out at the gate when we eventually get an electric gate. So that was a big boost, and they charged us a lot less than it would have cost us to do it ourselves or to put in a conduit so we could pull fiber in later. So that's all coming together pretty well. I think this is part of the rural broadband initiative, and so we were one of the first in the county to get the fiber drug in. So that was another trip, and then we had a trip yesterday, and Rick and Paul and Ray and RC and myself were all there, and we fixed a broken window that had gotten broken in one of the storms, probably a rock in the wind. And we got some of the additional Ethernet jacks put in so Paul could hook up his radio station on the radio console. And let's see, what else did we do? Ray and RC worked on the eCallisto antenna and got the system set up for that. And all they have to do is install the Adreno control system that's got new software coming from Ed Shade and Roger Oakey. And so there's a lot going on at the site. We got a lot of cleanup to do to get ready for open house, but we've got just under 2 months to get it all ready to go. So about 6, 7 weeks to get everything done for open house. So that's what we've been doing. So I see, I think we picked up a few more people, and I'll turn it back to you, Paul. Maybe Rick's got those pictures we could show.
Certainly got the pictures. Is it time?
Yeah.
Okay, share. That's not what I want to share. Someone else is sharing. Let's not be doing that.
I'm sorry, I was muted and I was supposed to show you this. This is where we cleaned everything out so we can put some more tower up there and maybe get some antennas up there. And there's another one on the other side of the building, just so people know what our building looks like. But anyway, I will stop sharing. Now I'm going to let Rick share. It's a fast moving story here.
Oh boy. I'll try again. Okay. Let's see. Is this what's being shared?
Yes, we can see it.
Aha. So we rented a small tractor a 4000 series subcompact tractor with a 10-foot bush hog on the back. It weighed as much as the tractor, I think, based on how the tractor performed, and started mowing the lawn. Now, the lawn was really just weeds. I don't even know what kind of weeds they are, but they varied from maybe 2 feet to 4 feet high. So it was a bit of a challenge to mow these, and it resulted in a few minor issues. But we have plenty of property to mow, so I just started in the morning and kept going. You see, this is where we park the cars. That's not safe because you park the car, your catalytic converter will light that on fire. So we had to knock it down. And it was pretty thick, not your average lawn mowing job. So this is just an effort to get started next to the driveway. Oh, you can't see the driveway? Well, that's part of the problem. So we got her going, and the first part that I started out to mow is the area where we park RVs. We have some RV plug-ins and stuff, and it's halfway up the tires in that area. And of course, and then I took a couple of swipes at the driveway to make it a little bit wider. Oh, there's actually motion. And as it gets close, you can see that it actually is mowing. And so this is very early on in the process. Just pretty much everything you see there got mowed in the process of doing this. That's behind the building. We ran into a little bit of a navigation problem right here where Paul is telling me, yeah, keep coming, keep coming. So I mowed the Ethernet line, and that took Paul a few hours to repair. But it wasn't my fault because Paul said, keep coming. About here, I got stuck on a hill of sand, and we tried everything we could think of to get it out. It's a 4-wheel drive tractor. You'd think it would get itself out, but it just dug holes. So eventually I sent Ray out to get my truck, and I'm on the tractor and Ray's driving my truck, and we hooked up a strap, and sure enough, we got it pulled out right away. Easy peasy. So I kept mowing for a few hours, took a break here for lunch. You can see how big it is. It's pretty big compared to the cars. And then I went back out into this field and spent the next, I don't know how many, 4 or 5 hours between this field and the bigger field next to it. And this is the small field mowed. Then I went and mowed the big field. And there it is. There I am about a third of the way through mowing the big field, and I'm way out there in the distance. It's a lot of acreage. But unfortunately, Bill did not finish taking pictures of me mowing this because we had 2 large storms, rainstorms, and I kept mowing, and Bill went back in the business building to stay dry. So, and but I got a lot of it done. You can see it's knocked down pretty good here. The dish actually is a little weird looking, but that's has to do with the camera, not the dish. So there you go. That's it.
Yeah, we got to give a great shout out to you for all the work and staying on the mower for 5 hours, and also to Rob McMasters who donated the money for the rental.
Yeah, I think it was more than 5 hours total.
Yeah, probably total.
Yeah, I think there was the morning, a few hours in the morning, and then there was another 5 hours just for that one field, the big field in the back. So we're about half to 2/3 of the way through the mowing process. If we could get another donation, I could finish mowing the north side of the driveway.
Yeah, I think we need to go back and redo the south side too because it's still too tall for
Oh, yeah,
purposes. Yeah,
yeah, it is.
and it grew up some since, and so within the next 2 months before open house, it'll probably grow up some more. We just
That's
had a
true.
really wet spring and summer, and we've never seen weeds like this at the site before. Go ahead.
I wonder if two questions. How about just disking it? And the other thing is, maybe we ought to hit up ARDC for a tractor.
Well,
First,
yeah.
first of all, if you disc it, we replace the weed problem with a dust problem, and we're talking dust that piles up in feet.
Yeah.
So
Yeah.
we have to plant some. If we disc it, we'd have to plant something.
Well, that's the other thing I was wondering about. If it were disked and planted with something, I don't
Well,
know, that would be similar to like Bermuda grass or something that would
yeah.
just take over and be a short cover.
Yeah,
I
that's
don't know
gonna
if I don't know if such a thing exists for that
well,
climate, but
yeah, the soil out there and the climate, we tried to grow some just some fescue around the bunker to hold the retaining wall back, and that didn't do very well. It's real hard to get things to grow. What grows really well is this ragweed that and all this brush that we were mowing out there. That grows really well. If we disc it, we'd probably disc all of that weed seed back into the ground, and next year it'd be even worse.
no
So,
doubt about it.
so I think the mowing or the grading is probably the best solution for small areas. We can drag railroad ties around and just drag the weeds out of the ground. But for the large area, we really need to mow it. I'm gonna see if I can talk to the road boss down in Handler. We used to have the county road boss would bring in his county mower and mow it for us, and we paid him something to the county to do it. And that worked out really well because they have it set pretty low and it really knocks the grass down. And they've got a really big mower, so they do it in about 2 hours. But small mower like this and having it set up so it doesn't get high centered is somewhat problematic. We need something bigger. But yeah, having a tractor. One of the reasons I designed the building with a garage was so that eventually we could get a tractor and keep it protected in the garage. So something to think about.
I'm responsible for raising money, and I was, just thinking about this conversation. I mean, we could try to plant some cannabis. That stuff grows really well.
Yeah.
Yep.
Yep.
The cannabis store down the road
The
went out
purpose
of
of this net
business.
is just radio related for Colorado and any current events taking place within the ARRL. This is a place to announce your hamfest.
Hey, Floyd, we're hearing your background there.
I just turned it off.
Yeah, he was
Thank
on two feeds at once.
Oh. Actually,
Yeah.
cannabis is not a bad idea, but you could turn a profit off it.
Yeah, we got a lot of
But
competition in Ordway.
Then you'd have to have a full-time armed person on the site.
Yeah, how much does the license cost?
I was thinking if you just let it grow wild, you'll probably get somebody to maintain it on their own without even us paying for it.
Yeah, they'll even bring a tractor, won't they, Chuck?
A baler.
All right.
Anyway, so let's
with a
move
name
on.
like Pablo, I should be heading that program.
Yes, absolutely. Well, anyway, moving along.
Okay.
Anything else, Bill? Or
Nope,
Rick?
that's it.
Right. There was something else I was going to say, but I can't remember what it is. It was so important, I forgot. Oh yeah, one more thing will probably. Well, I'll talk about it later on another time. Maybe we've got some other fundraising ideas. But in the meantime, I assume everybody got a invite to our all the member of what do you call it, our social, which is in Black Forest this year, which will be before the open house. And the open house, for anybody who's watching, is on the let me get the right date here so I don't screw up again. It's on September the 27th, I believe. Yes, September the 27th at Haswell. So mark your calendars if you're interested in coming. We got some folks coming from long ways to go to that. So
Yeah,
it'll be
Paul, would you reiterate you mixed two things there. One is the social, the DSES social barbecue.
that's
So
on the 6th of September,
September 6th, and
then
that's at Rick's place out in Black Forest.
right, and then the open house will be on the 27th of September.
Okay.
And then there's the ARRL contest, which is the weekend of October the 10th. So those are a couple of the key dates coming up in the next 2 months.
Okay.
All right. And with that, I see that our ham adapter, Alex, is there. And I wondered, Alex, are you ready to give us a little bit of a overview of what's going on with deep space these days? And I know Pablo is very interested in hearing what you've got to say, and a few other people as well. So
Do you
take
hear
it away.
me okay?
I can hear you perfect.
Okay, I guess I'm gonna share it now. Let's see. By the way, I already booked the tickets for the contest. Okay, let me know when you see it.
There you go.
All good?
All good.
All right. Well, good evening, everyone. This is part 2. Actually, I didn't update the date. If you look on the bottom, there is a 5/11, and today's a 8/11. So nice. So it's been 3 months since I presented the first part. So here we are on the second part where I already finalized the design, and we're good to go. Well, I want to kind of recap from the first meeting we had, presentation back in May. Maybe someone new joined. So what is a deep space network? So deep space is it's a network that meant to only receive and control the probes that NASA launched, and they will consider everything that over the Earth orbit that would consider deep space. There are only 3 sites globally. One is the United States, second is Spain and Australia. So it's 120 degrees basically. So each site covers one portion of the sky. The headquarters of the deep space located in NASA GPL. They are primarily who control all these sites across the world. So why we need the DSN, the Deep Space Network. So it's crucial for communicating and tracking spacecraft. So everything, once again, flies over further than Earth orbit. That needs to be controlled, and that's where the deep space involved. Once again, recap what frequencies are. There are a few bands. We're only focused on X band. S band is not that fun for us. Doesn't have sufficient data bandwidth for it. K band, as we don't have antenna that operates on K band, so we're kind of expecting operate an X band from our side because of good gain of the antenna itself too. So the focus primarily on the X band on the frequency range that allocated for a deep space network is 8.4 to 8.5 gigahertz. So there are a few current deep space missions, and we're going to focus on Voyager 1. Voyager 2 is actually active, but NASA has a trouble to communicate with. So it's still active, it's transmitting, but antenna is not pointing towards Earth. So we narrowed down to Voyager 1. It's the only one man-made probe that flying millions and billions of miles away from us. And the second, our candidate would be New Horizon. There's actually another one called Juno, but I'll talk about that later. So why we need to do DSN and what's so interesting about DSN and why we need to be involved in that? Well, Deep Space Network is a pure science. There's no amateur radio involved at all. Majority was amateur radio operators, but that's nothing to do. It's just science. It's something it's far, far away from Earth. And I want to highlight the one thing that, I mean, majority of scientists across the world are using the radio telescopes to receive some, signals from the deep space and from we do like pulsars, masers, quasars, and all that stuff. But we've never done something that man-made object that emitting signals, and we are man-made tools such antennas and its mutation, and we can receive that. I can guarantee there's not many people around the world can do that. So we can. Why not going to try? So as we already know that Voyager 1 is our primarily mission. So if we successfully receive the signal, we'll detect the signal. That would be a big accomplishment for Deep Space Exploration Society. And that's why I tried to tailor everything to that. But that's only one. That's not only one probe that we will try to receive. So this is the current status for Voyager. It's actually almost a light day away. It's been flying for 47 years, and this is just barely 1 day out. So, and one of the other things of why we need to do, because those probes will eventually die. They're gonna consume all the resources, and Voyager has a nuclear powered power source, but it will die eventually the next 5 to 10 years. So, and that's another reason why we need to receive it, because it's going to be part of the history. So as you can see, currently position for Voyager is 23 hours, 13 minutes and 28 seconds away from the Earth. It's flying away from our planet at speed of 38,000 miles per hour. It's about 17,000 meters per second. That's something number I used for the Doppler shift calculations. All right, can we receive Voyager? Once again, recap, I kind of squeezed like 5 charts into one. So yeah, this is the science data. I ran it before, everything matched. So yes, we can receive. So this is just initial data for us. And we will target all these probes to receive signals from. It's going to be Voyager 1. It's going to be Juno, and it's going to be the New Horizons. So those are 3 active. We're going to start with the closest one to us, which orbiting Jupiter right now. The signal is going to be enormous, as you can see, it's at 26 dB SNR, so it's 26 dB over the 0. So it's definitely good reference point for us. Followed by the New Horizons, but also as a Voyager flying away from Earth. And if we will be successful, obviously Voyager going to be our main candidate after that. All right, DSN system design. I already presented before. I kind of redesigned the system, kind of simplify, trying to find the best way to approach. And more than that, it's not just a separated RF system. It's actually a combination of multiple things that first time in my experience I'm implementing. So first of all, one of the features that I never talked about before is the feed control. So it's actually entire feed assembly with the RF unit is mounted on the stepper motor assembly that has plus minus 20 centimeters adjustments. So basically, instead of going back and forth, we try to find a focal point. And at those frequencies, we never done any tests, so it would be easy to remotely control. So I designed not only hardware and also the mechanical aspects, but also wrote the specific software for that. So pretend you have RF box that mounted on top of the assembly, and that assembly mounted at the feed point. So remotely, I can control all of that together. So another thing is the control ones or data processing unit. It's basically the brain that controls not only the stepper motor assembly and the RF unit, but also collects the data, controls the SDR, collects the data, stores the data, processing the data, it sends real-time data back to the shack. So as you can see on the drawing, on the diagram, basically you have RF system and control system and a stepper motor assembly located at the hub. You have only one fiber optic line coming down, and you have the control room, which all we need just any computers. No resources needed whatsoever because everything happening on the hub. Processing, receiving, plotting, everything. You're just normally remoting, like you normally remote, like Paul remotes his station from home using cell phone or his computer. It's exactly the same approach. So we don't need to have any sophisticated test systems up there. So, okay, moving on. Okay, system characteristics. So this is what I outlined because it's a real data that I got from the bench tests. So a system capable to receive 8.4 to 8.5 gigahertz. Total received gain is 55 dB. It's just a gain of the system itself. That's not considered the antenna gain at all. And I can actually tweak the gain and it's totally variable. So 55, it's a maximum, it's a lot of gain. So adding the antenna gain, which is roughly about 40, close to, I think, 50 dB. So it's 100 dB overall gain total, which going to meet our requirements to receive weak signals. I implemented the more like for future use, but once again, maximum gain is 55, but can be reduced down. Total noise figure system is 8 decibel. That's the total included down converter. I think it's pretty good for this system. We can fight for any 0.1 dB, but I think this is a very reasonable number. Consider we have a multiply intermediate frequency conversions. So real-time bandwidth is only limited to the SDR. Currently, I'm using the small SDR R2 AirSpy, but if you use any other like a B210 or any other, we can increase the real-time bandwidth up to 100 megahertz or 50 megahertz with Pluto and all that stuff. But really, we don't need that bandwidth at all to detect the spacecraft. So resolution bandwidth, I can go with 10 hertz. That's sufficient for our task. And polarization, well, I have two polarizations, and both are switchable and controllable. By a matter of switching the button in the software, I can go from the right-hand circle polarization to left-hand circle polarization. DC power, everything fitted through 12 volts, absolutely. So you can have a power supply in there, you can feed it from the control, it absolutely not matter, but the entire system requires 12 volts. And power consumption, I measure, it does not exceed to 2 amps. The entire system at maximum consumption is only 2 amps. The standby, probably around 1.1 amps, something like that. So that output is a raw IQ. So we operate and use only IQ data. So this is a concept how I want to mount the system on the feed. So on the right side, you see the hub, and then we have a mount that we normally attach to feeds, and then we have a computer module installed inside, or it can be mounted to RF assembly. It's not critical. Neither system is waterproof, so we need to avoid any weather conditions. One of the worst case, you can just put the like a back something on top of make it waterproof, but that's going to be system use only for the purpose and removed where we don't use it. So I'm not worried about that. So basically, what I have a platform. You'll see on the photos later. There was a platform with the separate motor assembly mounted, and then the RF assembly is mounted to that movable part of the separate motor. And the whole chassis needs to be mounted to the hub using like an L shape, something bracket like that. So I'll let the other guys to think about. I have a task, someone who can build that for me. I can provide the dimensions. So we know that the feed point from the hub is about 2 feet. So within 2 feet, we need to make sure that the system fits there. And I have adjustments about 10-inch plus and minus 2 feet to move back and forth. So this is IFU configuration. This is basically internal system. It's slightly different. I designed to feed the purpose and be simple at the same time. So instead of have 2 separate receive lines and the 2 separate down converters, I've used only 1 down converter because there is no need. After my analysis, I concluded that we don't need to simultaneously receive right and a right hand and a left hand polarization. Instead, we have just a switch between them. So that's why I implemented the feed 2 separate outputs with 2 separate bandwidth. I'm sorry, the bandpass filters. Those filters I built. I used one of the commercial on the market I found on eBay, completely different frequency, and I was able to tune it to the right frequency with the insertion losses less than 0.2 dB. So it took me 1 day to get there, but I got it. And then we have 2 LNAs, each provides about 22 dB of gain for each of the polarization. And it goes to the relay, a low loss relay. So overall losses on the front end of the down converter, roughly about 0.5 dB, which is insignificant based on the antenna. So we'll filter out the signals. So we're strictly on the bandwidth of the DSN system. And then we amplify it up by 22 dB and then put this down converter. Down converter has a built-in LO, which is 7.9 gigahertz. And it's sync and using the 10 megahertz external reference. So I don't use GPSDO because we don't need for that. Instead, I'm using the oven stabilized crystal, which I ran it and it gives extremely good stability. So it's on board, but I did implement the option so you can switch to external. It's also commanded by the software. You can switch to the external if you want to use any sophisticated reference sources. You can actually do that and supply that directly to the assembly. And then we have IF line output is 432 to 532 megahertz, which is every single SDR receiver capable to receive. So if you receive 8.4 gigahertz, your IF frequency is going to be 432. If you're on the upper band, 8.5 gigahertz, your frequency is going to be 532 megahertz. So it's only received, so we're not worried about the spectrum on band allocations at all. So this is the assembly, RF assembly. I didn't want it to make something for the magazine, so I just had whatever I had, used it. So it's basically aluminum box chassis when everything is mounted in one assembly, down converter, filters, and the controls, and as well as the SDR, everything. It's all one RF unit. It will have a cover on top right now to just test a stage, so you don't need a cover, but everything going to be covered, but the cover doesn't really do anything. It doesn't need to be. It can be open like that. So this is from the side view. As you can see on the bottom, this is the motor assembly. It's kind of hard to see, but there's a stepper motor with a rail. You can see there's the shaft in there. So the whole assembly moves back and forth using the stepper. So as you know, the stepper is very fine steps and I can control the steps. And I'll show the control software that I wrote. allow me to do that. So basically, this is the first time we can install something at the feed that we can actually remotely control to adjust the focus. And I'll tell you why and how we're going to do that. So basically, outputs, as you can see, is only reference out. So we can feed something else. I just added external reference out. And there was external reference input, which I mentioned we can supply 10 megahertz from our 10 megahertz system if it's needed, but doesn't really need it for this system. It's all self-contained. And all we need to do is connect two connectors. One is USB 3, which is gives you our raw IQ data. It's capable to transmit of over 5 gigabit per second over that cable. And then we also have basically control and power connector, which is combined. It supplies DC power and controls. Yeah, that's right. Okay, moving on. So MCCS, so it's basically monitoring, control, communicating system. I just name it, so you can call it whatever you want it, but for me it's MCCS. So it's based on the Raspberry Pi. Unlike before I mentioned I wouldn't use Odroid, but I choose to use the Raspberry Pi because it has a lot more features for me, and especially GPIOs that I will need to use this in the future as well. So it's a self-contained system. It's basically a microcomputer that converted signal to the fiber. So everything I just discussed, everything goes through the fiber optic. No coax cables involved, nothing at all, everything through the fiber optic. And at the same time, we can do real-time raw IQ data processing. So that box has computer and it also includes the stepper motor driver and the controls and some small electronic controls that I put it there to control the relay for the polarization switch and external reference. And also has built-in temperature sensor, so I can track my sensor. And this does not include also the current sensor. So I also implemented the current sensor, so I know what's the current consumption, tell if the system is healthy or not. So this is the box itself. It's literally about 10-inch by 2-inch size, 10 by 4 by 2. That's a small box, and it does everything. So everything is inside. So the main CPU and the function. So the Raspberry Pi, it's a 64-bit 4-core processor with 5.5 gigahertz speed, and has built-in 8 gigahertz RAM memory. So it's we don't need more than that. It's totally fits into all requirements for the system that will collect the data and work with ASDR data. So basically, I just outlined what the features are. Is Ethernet 1 gigabit connection, which I use to convert to fiber optic and back to the shack. We have USB 2. Currently, I use that for SDR just because the R2 does not have a USB 3. But if we have USB 3 like B210, we can switch to USB 3 and have 5 gigabit instead of 480 megabit per second. But for this particular purpose of the deep space network, USB 2 is totally sufficient. It has a Bluetooth connection as well, so you can have external devices connected to the Bluetooth. But I don't use that in the system. It's capable, but we're not using it. We have 40 ports of GPIO, so I can control in and out 40 different loads or collect the data from 40 different points. I use a few of them, but some of them are free, so we can implement in the future if we need extend and expand the system. USB 3, I mentioned we have 2 ports of USB 3, which is one currently used for the solid state drive. I have a built-in 256 gigabit drive to collect the data and store data for the raw IQ data because it's kind of heavy and requires some space. And Raspberry does not have internal space. It's very small, so it's just basically SD card. But I'm using an external connection and it has 256 gigabit, which is really. All right, so this basically outlines for the Raspberry Pi. Most of you know what's a Raspberry Pi. In the future, it can be upgraded to Raspberry Pi B5. Doesn't really need it for this particular case, but it's easy just to swap the one board to put another board. Has exactly the same coding, exactly the same thing. So it's all based on a Linux basic operation system. And I already mentioned all of this key specification of the board. Software. So, I mean, hardware was the easy part for me because it's kind of predictable. You can buy the parts, you know what to put, you connect, you test, everything works. But how can I do the software? Software is something, not something like you can just simply download it or just get something. No, software needs to be specific software. And you know, most of you in DSES know what means the specific software for the specific case. When you have a specific parts, you want to do specific functions. I want to tailor down. I don't want to use something commercially available that only utilizes 10% and other 90% is useless for us. So I decided to write the software completely from scratch, brand new. I had to learn Python language, which actually benefits in multiple ways, which is for my professional career as a scientist. It's very helpful to know the Python, and also for us, because now I can do any custom softwares for and not to be rely on anything. So identify sort of you know, requirements, what the software requirements going to be. So I want to make sure that it's a fully remote control and monitoring telemetry. So the software will allow me to do that. Stepper motor control. So I don't want to deal with the DC signals and going back and forth. I need to do everything remotely. Control stepper in a way, in the shape and form I want, with manual and auto modes. As well, put some data input variables. Like I said, go to there, read there, and go back and do that. RFU control. So I want to switch my polarizations. I want to switch external references or anything that I would consider in the future. And then SDR control. So the same software should control the SDR. And it's also the same software should treat the data. And same software should also be capable to plot everything. So, and also other additional features if they needed. So I had those beautiful requirements. Now I have to write something. So it took me kind of a month to get there what I got. So, and this is how, as today, the main control software looks like. So as a reminder, everything is stored on that processor computer. So nothing on the computer. So I don't really need any DSES computers at all. All I need to have internet connection, and any one of you can control this from home or laptop or anything, anyone within the network. So nothing is locally stored. So you don't need to have a specific software installed on your computer. Everything already installed on that small tiny box. So when I do debugging and programming, I remotely connecting to my unit and doing it from my PC. And I will demonstrate this because final portion of my presentation going to be actual demo. So we'll go together and connect the DSN system, and we'll do real-time receiver. So basically, this is the software. So I have two separate planes. One is a RF control plane, and the other one is a stepper motor control. So we have RF control as far as right now, because it's all can be changed at any time. I can control external software. So there are in a Linux environment, there is a software called KQRX. It's basically equivalent of any SDR softwares we use. There also there is control of the polarizations you can see, and then there's also external reference. I can on and off, switch on and off, and just not only switching is also give you the feedback back on there's a status bar on the bottom, so it gives you the information. So what's actually going on? Did I switch my system on? Is currently on? So there's a lot of visualization implemented in the software to help operator to identify what's actually happening. So we have telemetry, which tells me at this point it's just a temperature and a current, which is helpful to understand what my internal temperature, what's the temperature of my processor, what's my current consumption, is any fluctuation or something going on. On the right side, we have stepper motor controls, which is basically to adjust and move the whole assembly. And I'll explain later on the slides why it's so critical to have that. And other things is just we can store the positions. Let's say you can remove these 8.4 gigahertz assembly, but more assembly is still there. You can put hydrogen line, or you can put 1.4 gigahertz feed. You can use exactly same software to control and adjust your feed without going there, because you don't know exactly what the focal point is. There are a lot of factors affecting it. But this allows you to move feed back and forth to understand where my signal is maxed out, and that would be considered. So this particular plane on the right side is a multifunction, as it's not associated with the deep space network. That's a unique system that we can also use for 1296, EME, science, name it. And it can be reconfigured and reprogrammed in any way from you want. So, or if I forgot to mention, there's a button called measure noise. So this is already established function. I'm still programming, still adding new features. This currently, it's a noise measurement. And this is the first step you need to do to identify the system functionality. So I implemented noise measurement. So what is the noise measurements? The noise measurements is basically you measure the cold sky. It's actually fundamental everywhere in NASA. When I used to work, every single instrument is calibrated, but it's not calibrated on the Earth. It's calibrated in the space. When they point all antennas to the cold spot, where we know what the cold spot is. It's a known territory of the sky. And then we're going to move to the highest noise constellation or sun or something like that, any objects in the space that emit radiation in a wide frequency range, and we calibrate. So this identifies your dynamic range. So you understand, based on my receiver system and my antenna gain and everything, I expect to see this level of the system, and that's how system calibrates. Because we had previously so many issues with in EME especially, or identify, we don't know what's going on. If the system operates and our dish is fully functional and the feed built properly, and you know precisely what you should measure, this noise measurement will help you out with those measurements. So basically, this is what it was. I already done this in past for the 1296. When you point antenna to the quiet area, which is normally on a sky map identified as a dark, as more darker it is, as a quietest, basically there's nothing. In that particular direction of our Milky Way is absolutely nothing. As you can see, there's a hydrogen line, and there's our Milky Way, and then there's noisiest areas like Sagittarius and Cygnus. So those are the calibration points for us. So when we can move antenna, instead moving antenna to sun, when it can melt our feed, we can move antenna to there and a measure and also moon. So, so I wanted to have this implemented in my software. So, and this is how I do. I click on the measure software, and then I have everything is a Linux and using terminal. So just don't be pay attention on that. It's basically some variables I implementing in the software, and it basically tells me, okay, point antenna in the cold sky. So it's first sends the data to this SDR receiver. Once again, doesn't matter what SDR. Currently, I'm using AirSpy, but it can be any. So I send variables to my AirSpy. Hey, tune your frequency to 452 megahertz, and there's a low frequency 7.9. So make sure your real frequency at the plotting gonna be 8.4. So even though it tuned for 452, it assumes this is 8.4, which is tracks the Doppler from that frequency. The rate is 2.5, which is standard for AirSpy, and gain set to 20. Once again, as those variables you can always change. Resolution bandwidth according to the FFT scan is about 76 hertz. Scan time I set for 20 seconds. I want to scan the particular part of the sky within 20 seconds, and pretty much it. So when I've done this, I get cold sky, and which is the left plot, and it's plotted. So you see within 20 seconds, I've got roughly about 50 minus 57 dB level, which is pretty much the noise, the system noise at this point. It's the cold sky. Then I simulated the object noise. So I put like some Sagittarius representation as form as my generator, and the right side plot tells you this is my noise. As you can see, it's 37. So after all this calculation, software does your final data. It's called Y factor. So now we know our system noise, our noise is about 19 dB, which is exactly matches what do I need to see in this particular part of the sky. So when this is performed and we match the numbers, we know at this point the system is fully functional. We're capable of receiving the signal, not just a blindly point antenna to the Venus and just cross the fingers and hope something will appear. We need to know that the system is healthy. So same thing what the most EME guys doing, they verify the noise of a sun and noise of the moon to identify. So we have this implemented. Now, when it comes to actual receiving Voyager, we can use as SDR GQRX software, which already built in. I already have this available. It's basically software that most of you already used to use it. It has standard features of any SDR receivers, which you can, adjust, tweak anything, and get what you wanted. So without me creating anything, it's already exists. So as is, today's system can be installed and used with using SDR GQRX software. So we can detect any signals in the space within DSN frequencies as today, as I speak, using already implemented system. The option 2 also implemented, and I demonstrated this last time on the first part presentation when I used GNU Radio protocol, where we visualized, and we created the algorithm that allow us to do the spectrum, and I demonstrated the last time how it works. Well, it's still working, it's still good. Now, problem with the GNU Radio, it's a sophisticated environment for the programming and creating a receivers based on SDR, but it has so many features that we don't need. So those features, unfortunately, consume the resources of the processor. So the software works, but it has significant delay, which I don't like it. So in asking myself, why do I need the software that only does 10% for me? Well, I can tailor everything and narrow down to specific. And now what the option 3 comes, custom software. Why not going to write the software that exactly thinks like we want? Let's say Voyager. Click the button Voyager, and it does exactly scripts and plotting, post-processing with the proper Doppler shift, everything. And then you press another button and goes to Juno or New Horizon, and already adjusted the frequency, adjust the Doppler shift, everything, and plotting the certain way. A standing operator trying to understand the science behind what you're doing using SDR, you can actually program this and have an easier interface. So I tended to go with the custom software option 3, which I started doing yesterday, and I've got already 20% accomplished, but there's a lot of debugging going on. And that's probably because we don't have immediate date yet. Nobody told me, hey, tomorrow we're going to install DSN. Well, we're going to decide which day we're going to be able to do that. So I'll try to make sure that I have a sufficient time frame to finalize the software. But as I said, as today, we can use it as is without implementing anything. So what would be our first attempt? So definitely, first of all, the workflow going to be, we're going to make sure that the system is fully functional using the noise measurements already implemented in the system. We're going to try to receive the closest signal from the closest object, which, as you can see, is the Juno, which is currently orbiting Jupiter, and then it's about 444 million miles. Then, if we're successful on that, and I know we will, because a lot of people that uses the very small, which is 3-meter antenna, just 10 feet antenna, and they are capable to detect a signal. So with our dish capabilities, it's going to be 5.9++. So I have no doubt at all. 1 second, please. And the second attempt is going to be New Horizon, which is it's the one of the space probes that following the Voyager. It's currently 5.6 billion miles away. So we definitely need to receive that one as well. And when we're successful on both, we will switch our attention to Voyager 1 and try to do that. So first attempt can be executed September 2025 based on the current situation where I have. So by then, probably I also try to finalize the software, the option 3. So we have 3 different options to execute. Exact date, I don't know. So there would be some action items that I identify for now. For me, is to finalize the software, as I mentioned, and run all scripts, make sure there's no internal bugs or something like that. I spent sufficient amount of time doing it, and once again, just volunteering doing that. Also continue RFU and MSSL bench test, because I want to make sure the system is reliable. It's been running here for days. I turned it on and was running back and forth and tried to track the temperature and any conditions, and run after 5 days operating. Is my processor lagging or something going on? So I would need a few volunteers to do a couple things. First of all, we need to fix the fiber optic line. We need to have 2 lines. That's one of the things that we already know, and that needs to be done. The second is we need to make adapter plate for the feed mount, because I don't know the distances. I don't know how holes are separated from each rail on each side of the hub where we normally mount the feed. So basically, I have a platform. It's about 12-inch long and about 6-inch wide. So this platform needs to be mounted on sort of rails that's attached to the hub. So it's going to be sort of like L-shaped bracket, but it needs to be reinforced. So we don't have any tilt or something it's shaking. So it needs to be kind of maybe boxed, maybe like a box instead L-shape. So I'll let mechanical guys, maybe Roger or something, or Ray, someone can think about so we can do that, because that's also going to be used for anything else that's not tailored to DSN, because the whole assembly comes out and then you have a whole platform. You can attach anything you want to it and do exactly the same controls moving back and forth. So the panel needs to be around the focal point. So we know that's approximately the focal point. So we can move in and out the feed for the optimal focal point.
Alex, does that 12 inches, does that include the frontal antenna as well, or is that in addition to the 12-inch package?
So let me see, go back
I
to,
think you said 12 inches.
so as you can see here,
Oh,
right?
yeah, there you go. Uh-huh.
So you see the bottom, it's actually your 12-inch. So my vision was basically you have platform, whatever it comes, let's say 2 feet, right? And then you have this mount that's going to be moved, adjustable. So you can have
Right.
a rail set of bolts, right? So you can actually move, depends on the size of because this one is particularly small. This is the whole assembly of this. It's a pretty
Yeah.
tiny. It's
Okay.
8.4, so it's pretty small, right? So you
Right.
can put it and mount it on the platform. If you use 1.4 gigahertz, you get a mount and different, you can adjust that. So the platform itself, the bracket should accommodate all feeds that we currently use. That includes 1.2, 1.4, and 1.6, and as well as 8.4.
Right, because right now we believe that the focal point is about 2 feet from the hub face,
Correct.
the lower hub face. And so what I was looking for was, does this accommodate with the bracket, the L-shaped bracket or the holding assembly? Will the center point of this be about at that 2-foot position once it's all assembled? And then it would go in and out from that 2-foot position in front of the hub. That's a
Yeah,
good
so
example. So if you go from the feed back to the hub face where the bracket is tied on, that should be 2 feet with this at the center point.
yeah, so I guess whatever you think is the best way to do it. I mean, 2 feet, you don't really need, I guess, 2 feet. You probably need to be shorter than 2 feet, but 18-inch or something. Maybe
Yeah, I
a
was
little
thinking
bit more.
if this is it, if the center travel of this
Yeah.
assembly were at 2 feet, then you'd be able to go in and out from there.
Yeah, so we say this staple motor assembly, like identified like a black collar, like a U shape kind of, right?
Yep.
So that can be adjustable. You can slide this along that chassis, right, until your feed point is matched to feet, right?
Yep.
And then from that point, you can move in and out the feed assembly, which is identified as RF assembly, for adjustments. So in this case, if you remove this assembly, put in another assembly, you're still gonna meet your 2 feet point, but it's gonna be different mounting holes on the same chassis.
Sure.
So
Okay.
you just need somebody to go on a hub, and because I know Ray last time built a custom mount for the feed for Eve project. So something like that, because I don't have those distances, it can, because I use the 1x1 inch aluminum angle, so which is kind of gives me the strength, stability. So my assembly is 12x6. That's what I have. 12x6. It's the stepper motor assembly, and everything goes on top step motor. It doesn't matter in this case.
Very good. Second question I had was, can we use a reference object, either terrestrial or near space emitter, to calibrate the focal point? Because you sure don't want to be calibrating it while you're trying to receive the satellite. So is there is there some 8.4 gig reference object that we could use that would be a stronger object to calibrate on? And we could even do that on a terrestrial basis, but the idea would be that we get the focal point calibrated before we attempted the satellite.
Yeah, we can pick up any any objects that emitting noise, and it doesn't really need to be an 8.4 gigahertz. So we can use any other frequencies to do that, whatever the highest, because what's important going to be is, first of all, the focal point, where focal point is, right? Because we know we can move, because I want to start with the moon noise, because the moon noise is less harmful for us, right? If the base of our system, let's say 8.4 gigahertz, if you calculate the moon noise, it's pretty significant. So we definitely should detect the moon noise, right? If we estimate it based on our performance of the dish performance and the received signal, that the noise should be around 6 dB, if we point antenna, try adjust the focal point to maximize the signal and to see what we at, how far we are from there, right? And that will give us idea, hey, system is fully functional, the focal point is here. And we can repeat this on 1.6 and 1.4 gigahertz using, let's say, Sagittarius constellation. That's pretty noisy on that frequency, a hydrogen line signal. So we're not limited now, because last time I had to go back and forth, slide 1 inch, go back, it consumes time for no reason. Now I have everything is remotely controlled and not worried about it all. So we can implement this concept for any feeds and any measurements we have.
Very good. Okay.
Any other question before I go to do demo?
I had a
question, Alex.
where you have several Mars probes that transmit on the 8 gigahertz X band, so, and they're closer. So maybe for if you need a specific frequency in the X band, then maybe you could try to adjust your focal point with detecting some of those. That should be a stronger signal.
Yes, and I know some of the amateur radios guys done actually on Mars rovers receiving, because X band is it's a common frequency, and a lot of even Chinese spacecraft, the moon rovers, they also operate in that frequency. So it's a standard for deep space network, and that's everything that operates in 8.4 to 8.5 that currently is on the planet or rovering or flying or does some missions, we can certainly receive. So we're not limited to 3 probes that I identified before, but it's just a good start for us. And I know that a lot of other people already successfully done it. So it's a good reference point for us that we can try. And then we can explore any others. As many objects we're gonna receive and put in the list is better for us. So definitely, yeah, we're gonna do that. Any other questions?
I have a quick question. I apologize if you probably have covered this before, but how are you implementing the left and right-hand circular polarization in your feed? And secondly, did you consider some maybe active temperature control for your LNAs?
So I think this is the best picture to see. So I'm using the feed is a septum feed. So it's one of the commercial feeds. And by the way, I forgot to mention, this is feed that being donated to Deep Space Exploration Society by Paul, W1 gigahertz. So he donated feed and donated the converter. The converter is very old, and I found no reason to implementing. So I'm using more advanced down converter that has way better performance. But we have that donation as well. So it's a property of Deep Space Exploration Society. So I'm using the septum feed that has a right and a left circle polarization. It's exactly the same type of feed and concept like we use for EME, when one side is emitting a right hand, another one is a left hand. And we have a septum in between the polarized septum that provides the isolation between 2 ports. This one being used for commercial application, 8.4 gigahertz. So it has the greatest performance, and I decided to use. So as you can see on the photo, one side is a left-hand polarization, and other side is right-hand polarization. And then we have a separate chain of bandpass filter and LNA on separate on each of the polarization. Does that answer your question?
Yeah, it does. And the second part was, did you consider some type of active temperature control for your LNA?
Yeah, well, that is certainly going to be helpful to reduce the overall noise figure. But I'd like to have initial data first. So we need to make sure what are initial data, because right now I kind of rely on the data sheets that are being provided to me for the LNA. I know what precisely my losses before LNA, which also contribute to the temperature characteristics, and as well as a down converter. But that needs to be yet verified in actual application. When we're going to verify, there are a few options we can implement to reduce the temperature, to drop the temperature of LNA, to increase that. That's probably going to be one of the considered options if we will not be successful receiving Voyager. Because Voyager is a good starting point for us to verify maximum performance of the system, right? Because that's the minimum possible signal. The calculations show that the signal is -2 dB SNR. That means it's -2 dB below the noise. So you're not gonna be able to see this on the plot in real time. But we will need to capture over and over and over with the averaging algorithm to allow us to detect that signal. If we will not going to be successful, definitely we try to implement by reducing the noise of the system as much as we can, and dropping temperature actively obviously going to help.
Thank you very much. That was fantastic. Thank you.
All right. Any other question? We'll probably have question when we have demos. So you might.
Yeah, I have a quick question about the Y factor method. To your knowledge, has anyone done that on the DSES dish at any frequency? Or gotten an estimate of the efficiency?
Oh, I'm sorry, what was the Wi-Fi question?
Well, the cold sky ratio idea of doing noise figure measurement. Has anyone done that with the DSES dish, on any frequency to get an idea of the efficiency?
Well, I'm not sure if anyone in DC has done it, but I've done it using the 1.2 gigahertz CME, and I was not happy of the results. Since I was using the 1.2 gigahertz EME test system, and calculated data show that I supposed to have a certain amount of dBs, we having this gain and everything, but I never was able to get to that number. I think at top of my head, we had over 17 dB difference, and that's something that red flag for me, because having 1-2 dB it's fine, but having 17 dB or even more than 10 dB, it's a red flag. So I didn't know what causing that, and I didn't have a proper tools on doing it, because one of the obvious things is going to be I'm on focal point. So we run numerous of laser measurements, try to identify the shape of parabola, try to identify the FD ratio, trying to ensure the focal point is correct. We've done everything we could, but yet still with that, we had some issues. So that's why I try to implement as much as possible in software features and mechanically, like adjusting the feed, to be able to collect as much more data as possible. And one of the things I'm going to do, actually, I have very small mirrors. I bought like 200 small mirrors that are adhesive. So we can place these mirrors on the surface of the dish at a certain point, and we make sure we're getting the reflection to the feed point and a certain size, so it's not spread it. And that's what it tells us it's supposed to be antenna being built well. So I don't expect it's going to be all over it, but for verification purposes, checking the box and just forgetting about this, we'll do that. So I don't know exact efficiency, but we committed to do as many experiments as possible, because that is helping not just for us, but also scientists as well. Because we're assuming this is the performance, but we don't know is the greatest performance? Is that what's supposed to be? Or it is what it is? So we need to answer those questions.
Thank you.
Okay, I gotta stop sharing that screen. I gotta have another screen to share, because I'm gonna remotely connect using my remote connection to the my computer. I lost the share button. There we go. All right. So let me know when you see the screen. Do you see the screen?
Yep.
See a blue screen.
The blue screen?
Yes.
Do you see the login window on the screen?
Yeah, it's the
Yeah.
BNCX login.
Okay. Yeah, so the part of the problem is that I'm using the wide, ultra wide screen. So do you still see the screen, right? Or
It's still there.
okay. All right, so I'm gonna log in. So basically, this is I'm simulating how I'm gonna be in the shack. I can use my laptop, or any one of you can use your laptop. So it's basically login. I'm using the IP address. As you can see in the top, you'll see it's the IP address and a remote desktop connection. So I'm using the Windows remote desk connection, connecting to the Linux environment, because that's not the Windows. We're gonna connect to the Linux. So I'm gonna enter the and then I'm logging into the system. So you're supposed to see the desktop. Do you see the desktop?
A picture of Voyager elongated.
Okay, perfect. Yeah, I'm trying to, how can I
Kinda
see what I,
stretched.
yes, because, yeah, so when I move, you can see it, so it's good. Because it's a widescreen. I like to use a widescreen because I can allow multiple windows when I do programming. So anyways, so I'm logged into the system. So I'm currently inside the deep space network system on the main computer. So the main computer has scripts. So to simplify everything, I created the batch file. As you can see here, it's a star DSN. So basically, it's the startup algorithm where a lot of separate Python codes are executing in a specific sequence. So it's easy for me and for everyone, instead of just launching one another code, and running because I have a virtual environment inside the Linux. So it's kind of too much havoc even for me. So I created just one file that executes everything for me. But everything starts from programming, and you go to MU, and I want to show what we're starting from. So basically here, so I have a multiply Python codes, which each will represent a noise measurements, Doppler tracking measurements, and DSN system. So it's just a code. It's too boring. So we're not going to go through this because that's not interesting. Interesting what's going to happen. So basically, I'm gonna execute, and the window tells me, "Do you want to execute?" I said, "Yeah, sure." So, and I'm connecting to the real system. So it just executes a lot of scripts and commands to launch packages and libraries and all kind of stuff. And when it's finished, it will launch the software. There we go. So also one of the things, it's kind of very small font, but I have a homing procedure built on this. So basically, every time you launch the system and power up the system and run this application, the motor tries to find where's my home. So basically to 0 point. Why? Because it's a stepper, right? Everything can go wrong with the program code or something, and the motor can override. So we have a physical stop with the switch. The switch is actually a limit switch. So every time you power up, what just happened, because you don't see the system, the motor starts moving until it reaches the home position. And when it reaches the home position, it tells me about the 0 position in the software. And this is only when it launches the software. So here we go. We're software. As you can see in the status, is saying ready. So that means the system checked everything. It's a self-check. Everything is fully functional. At this point, I can control stepper motor. I can control my RF system from here. So if I want to select right-hand circle polarization, I click the button, and as you can see in the status bar, it say right-hand circle polarization is active. So it's a feedback coming from the system that I executed this for you, and the button become green. So it tells the operator, hey, we're on the right-hand circle polarization. And it does pulse because the relay is a latching relay. So it just press the button once and does the pulse. Another thing I can hear like a relay clicking here. And we're on the left-hand circle polarization. So by switching this, the system goes from one polarization to another, switching one port of the feed to another port. So I also track my temperature. It's a temperature of the processor currently, and current consumption of the system, sort of like a telemetry. I can add many points of telemetry. I don't really need it. This is too relevant and important. Also, I can use external reference. If I have, let's say, 10 megahertz like we used to have for EVE, and we want to supply this rubidium signal, I can connect this to there and I can command it. So we don't need to go there and switch cables, nothing. It's going to go from internal reference into the external reference and going to lock the SDR, which you can see on the terminal window when it's locked or is not locked. So basically, that concludes the radio control tab, except measure noise. We can go through that in a minute. And then stepper motor control, basically the top portion is jogging. If I want to manually add it, let's say I'm tracking something and do it manually. I press forward button and the motor drives forward. And then as you can see, reverse. So let's go to 200 position. So as you can see, motor position 200. So I don't know if you hear or not, I put 4,000. So the motor is running. So the feed currently is adjusting. So it's moving to the position. So number of steps is represent the millimeters. So basically 4,000 steps means I moved my antenna by 4 centimeters. So, and I move towards it. So and then I can save this position 1 and I can name it as sun. Oops. All right, so I saved position as a sun, but realistically, it's gonna be DSN. So then we're gonna move motor to, let's say, 6,000. Go to position 6,000. You can see the numbers are changing until I started moving forward. I'm gonna save this. I'm gonna save this as hydrogen. So basically you can save any feeds. I have 3 feeds right now, but it doesn't really matter because you can add as many as you want. Presets is a matter of how many buttons I can feed there, but this is just an idea, right? Where I have the maximal focal point based on my DSN system, and when I install the hydrogen line receiver, how the system gonna, where the position for the feed gonna be. So it's saved into the file, text file, and when you load it up, the software, it's gonna recall that data from that file. It's easier way than use EEPROM and save this in the memory. I rather use a text file. So you can change the speed on the bottom, so you can do faster, you can do very slow. So if I want to be very fine because of the wavelengths, like 8.4 gigahertz, the wavelength is very small. So I want to reduce my steps and put in more delay, let's say 5. So my motor going to be moving very slow. If I want to do faster, I can adjust to half. So basically this is, go to 0. As you can see, here's a status on the right side. It tells me what my current position of the motor is, compare where I'm looking for the target. So it's basically going to the 0 position right now. And I see the whole assembly sliding back and a stop. All right, we're here. All right, so we know we find perfect spot. This is what we want to do, measurements, right? So first we adjusted our feed to understand where I'm supposed to be according to numbers. Now I want to actually verify is as it matches. So I'm going to click on measure noise. And here's a fun start. So first of all, I'm going to verify what's my frequency is. So in this current is my frequency is 452 megahertz because that's my IF frequency for Voyager frequency. So I click on that, okay. So it's asking me what's my sample rate gonna be. R2, our AirSpy has 2.5 megabit. So I'm gonna keep that as is. So what the gain's supposed to be. So those are settings for the SDR. If you can use B210, you got to use a library for it, piece of cake for me, and then it's going to send the same commands. What kind of variables do I need to set my SDR to? So I'm fine with the 20 dB. And then how many seconds do I need to do measurement? So in other words, how long do I need to sweep on this particular spot and collect the data? You can do 10 seconds, you can do 20, you can do a minute. And this is helpful. If I do Voyager, I'm gonna be, or Moon, I'm gonna be a lot more dwelling, so I wanna have more time. So I can set this 60 seconds, let's say, but will be 20 seconds for now. So, and this point, as you can see on this window, I don't know if you see it not, I don't know what kind of phones are, but it tells that the data was sent to SDR, I'm connected, and I'm ready to execute. And I'd like to run the cold sky. So at this point, you're gonna move dish into the cold spot. Since we're moving in a space, and the space is constant for us, but we're moving, we just need to see what the elevation and azimuth gonna be where we're gonna move our antenna. And as soon as we point antenna, we just click enter. And what it does, I need to slide this. So what it does, it's scanning in real time and collecting these points. Basically just a noise because I don't have anything turned on. It's just a system noise at minus 60 decibel. All right, so it finished scanning. I say, okay, we're done. We're at the minus 60.92 decibel noise. If you see, it's kind of erratic up and down, but look at the scale. Your scale is literally 0.7 dB resolution. So I have a dynamic change of X. I can set, it's going to be flat line. So it's not like what it is. It's just a 0.7 dB magnitude. So that's where you see these lines. So it gives you more precise data points than just a flat line. We don't have resolution. So that once again, you can say dynamic. I'm sorry, you can set static axis. So in this point, I'm going to simulate the noise. So it tells me point antenna to the object, and which is going to be, let's say, constellation or moon, and I expect to get 10 dB moon noise. So this generator just simulates the signal on 8.4 gigahertz for me. So this is the representation of the Voyager. But if we're just measuring the noise, it doesn't really matter. So I'm going to set this frequency. I'm going to turn on about 3 feet away from the system. And it's minus 27 dBm output. And I'm going to click enter. So as you can see, we start scanning. And here's a plot. Honestly, I don't. Oh, 1 second. I see. Why I see no difference? I see like, oh, wait a minute. I don't see the noise. Guess why? Because I need to be in the right-hand polarization. Because my left-hand polarization currently off. I blew the preamplifier accidentally. So I have to repair it. And I forgot about it. And I was doing demo. I switched to left hand. It's not connected. So I have to go back again and launch the script to demonstrate. Very quickly. All right, do it again. Point antenna, cold sky, click OK. So all of this can be, if you see that something needs to be added, or we can modify or add something that's useful, not just for us, DSN, but something that you think is helpful, let me know, because I can implement anything, and you can just simply add the tabs to the existed. Okay, we're here, we're done. So I'm gonna turn the signal on now. All right, now I'm transmitting and gonna run. All right, now definitely you see the difference, right? So now it's a minus 37 decibel. So it's gonna be 20 seconds. And after that, it's gonna plot everything for me, because this is just a data collection, not important. And here we go. This is your final data. I kind of wanted to put everything together on a quad chart, but once again, it's for me. But anyone can update this in a way. But so basically, we have a cold sky measurements. We have basically the amplitude in the time domain. So we swept over 20 seconds, and we see how amplitude was changing over 20 seconds, and variations are not that big. I don't have that source locked, so it's drifting. So that's where you see the line going down. This changes the level. And then this is object noise. Basically, that's what we measure, simulated. This is the Y factor. As you can see, like a blue line is kind of flat line now, right? Because you have different resolution here. And then simple calculation, it gives you the noise. So the measured noise now is a 19.8 decibel, which is the difference between cold sky and object. And this is the number what we should look for, because we know if with 18.2 meter antenna with this gain and this current situation, the noise expected to be of this source, particular source, around 20 decibel. And with point antenna, we did calibration in cold sky with point antenna at the constellation, and we're 19.8. So it tells me we're off by 0.2 dB, which is totally insignificant. So and that's the easy way to calibrate your system. Any system, it doesn't matter. It's not tailored to DSN. We can set any frequencies, use any receivers, any conversion, as long, because this software only controls SDR. What kind of SDR you put it there, what kind of frequency range, it doesn't really matter. All these variables, you can set them prior. So basically, we just represented the simulation, but I'm working to writing the software. We're gonna have additional button here. We're gonna have ability to do testing for Voyager. So instead of me putting all these variables, because Voyager flying away from us at a speed of 17,000 meters per second. So it's a minus 17,000 for the Doppler. So I need to put that variable to calculate my Doppler shift to correct my frequency at the SDR receiver. If I want to receive signal from Juno, the Doppler shift is different because it's closer to us and the speeds are not that crazy. So if you don't have this and you need to use one application, you need to enter all these variables by yourself manually. So I want to get out of this. I want to have every individual object have a separate button that's going to execute the script for me. If you want to rewrite the script or add some variables, it's like you see this windows popping up for me. It's already preset in the file. So anyway, I close this. And this is how we have right now. Once again, is executed just from one button, but realistically, it's a 4 scripts running on the background. And if I don't want to, I already done measurements for the noise. I'm certain system is functional. What's next? Oh, receive the actual signal. Since I don't have option 3, as I mentioned, I don't have my software ready yet. I'm going to use built-in software that has a Linux environment. And I'm going to close it. Close it. So, all right. So it's going to launch the software. So here we go. Oh, you see it? Okay. So it's already set the frequency to 452, 432 because that's my frequency IF. So I click start. And since I'm transmitting, still transmitting, you see kind of spectrum right here. So I'm going to zoom zoom in. Okay, so this is my spectrum, real-time spectrum. And I kind of put the marker what wager is supposed to be. So resolution bandwidth is 76 hertz, but we can actually lower it down to 10 hertz if it's needed. But I don't think that's going to be helpful, but we have ability to tweak our resolution bandwidth. So I'm going to turn off the source. And as you can see, spectrum is completely clean. So this is no harmonics. So this is the raw IQ data. That means there's no modulations, there's no post-processing, nothing. It's a raw data coming out of SDR. And that data is heavy. So if I'm going to click, if I'm going to stream this data, just stream through the channel. If I have receiver on one side and I have SDR on the other side, I have to now stream this enormous data, which I don't want it. I want to do everything in one place. So that's why I have a computer and SDR next to each other, USB 3 connection. It's 5 gigabit per second. So the IQ data streams to the computer, stores on 256 gigabit data. And the post-processing is another script in a Python. You click and you post-process. Because the Voyager wouldn't be visible on the screen. You're not going to see it. You're not going to be able to detect. The reason I'm launching this software is to stream raw IQ data and store it so I can post-process using the scripting. So this is the sophisticated way of doing something we've never done it before. And this is just the beginning. So if you don't want to use this, simply click on this button and close this. I can put as many applications as possible and implement in the software will ultimately become a control software. So once again, I'm doing this from my environment, from my Windows computer that I'm doing Zoom call right now. And it's just a matter of button. So I'm gonna close the system. But before I'm gonna disconnect, does anyone has any questions would require me stay in the software?
Yeah, Alex, could we use PuTTY to connect?
Use what?
PUTTY, PuTTY?
Oh yeah, for sure, of course. You can connect to, this is using the SSH, right, the shell connection. Yeah, you can use PuTTY, no problem. You can use IP address or any remote software, because if I would have now a static IP address, you can connect to the same box right now from your home. Only you're going to have a delay, some latency because of the internet connection, but that's only one aspect. But having like, I don't know, 200, what was it, 200 feet of fiber optic cable between feed and the control, there would be no latency at all. So it would be real time, like you operating in the computer is exactly operating in the remote. So my main goal, and I already was talking about this many times, I do not want to have any RF cables. No, let's not go anymore. When we deal with weak signals, everything needs to be remotely controlled. The fiber optic is the solution. So we had initial concern, how much data we can transmit through the fiber optic. I don't care. 100 megabit connection for the remote desktop, that's fair enough. I don't stream IQ data back and forth on the fiber optic. No, it comes between SDR and the computer within assembly, which is 1 foot away from each other. Any other questions?
Yeah, Alex, do you have a calibrated X-band source, like noise source or signal source, so you can measure that Y factor in the lab?
It is possible. I mean, you have two generators and do that, but normally you do Y factor at the antenna, because the reason to know the Y factor is to compare the antenna performance, right? Because I can do bench test. I've done this million times as a part of the EMC MSI compliance and mil standard 461 government requirement. But it's not nearly when you do actual system. So when I build a system and I have an EME system here in my backyard, and I know precisely what the antenna gain is, the FD ratio, and what the frequency operate. Those are 3 variables basically you need, right? So based on the known source, and source like sun noise based on the SFU index, right? The sun flux unix, and measured at 10 gigahertz. We know precisely at my location right now the sun flux is 178. So I calculate 178 and base my received data. So it estimates if I point antenna in sun, and a point antenna in moon, and a point antenna Sagittarius or Cygnus is any constellation, I should measure this numbers. So the very famous calculator is a VK3UM calculator, that everyone across world uses for DME calculation. And then you do measurements like Y-factor measurements, and then you see how close you are to the estimated, right? So the bench tests in the labs, it's helpful when you want to verify performance of your receiver. Let's say I want to measure the noise. My down converter noise is supposed to be 8 decibel, but maybe it's not 8, maybe it's 10, because most of us always ignore the fact that the data sheet has numbers called typical. So what is supposed to be typical? Is a typical that came from the manufacturer of the components that recommend that this is the recommended noise. Typical does not mean it's a real. So that's why I don't trust on numbers. You have to verify that. So the batch test is good to verify RF performance within assembly, but the Y factor based on your antenna, because antenna factors are crucial that affecting this overall Y factor.
I guess the point I'm making is that you'll be able to have a solid number for the receiver noise figure that then you can back out and figure out what the antenna is contributing when you measure it.
Yes, good point. Because when I calculate, I do consider the noise figure, right? I do consider standard variables like a ground noise. What's my typical ground noise? All those kind of factors, right? And let's say I measure the system, and I don't know those numbers are precisely, but if I within the expected value, all other tolerances would be tolerances of the noise, right? So you always have that delta. You always have tolerance. You can't precisely say that's going to be 0.001, and you're trying to chase that 0.001. It's never going to happen. But if you are too far away from the calculated estimate numbers, you need to understand where exactly you lose those numbers. I made one typical mistake every time when I try to do sun noise measurements. I got SFU and I measure it in the afternoon. And I'm doing these measurements, try to chase this missing 3 decibel. By the time the sun is moves and SFU drops, but I'm still using the initial number. And I'm trying to chase, but now I have 5 dB difference instead of 3 dB. I'm like, what the hell happened? But the problem is that the sun is degrading. It doesn't have the SFU number. So you have to constantly verify this SFU number to calculate what the real data output is going to be. So sometimes it's complicated, but if you understand all of that, so that's why I don't want to rely on myself using the software. I want to have all this data gathered for me, placed in the software, calculated, and given the final data based on those variables.
I have a quick question on your software polarization selection. I assume that that's the actual receiving polarization and not necessarily the feed polarization, correct?
Yeah. So with the septum feed, if you ever had experience with the septum feed, so the septum feed principle is it's a two probes on each side and have a polarization septum between. So if one right hand and one the left hand, but this is reference to the feed itself, but it's different when your wave it's reflecting. So let's say you have a plane wave as a right hand polarization, and hitting the dish surface is actually switches polarization to the right to the left hand, and it comes as a left hand polarization to your feed. Now the left hand circle polarization probe picks up that signal. When you transmit in the right hand, it does a positive way. So when you transmit right hand from the feed, when it reaches the surface of the dish parabola, it switches polarization to the right hand and radiates. So this is how the principle of EME works. So feed has 2 physical ports that each one is a left hand because on the right side and a right hand because on the left side. So by the time in a plane wave in a space, we deal with the 2 separate polarizations coming from 2 separate. So why two polarization really needed? You know, the antenna on the Voyager and any other objects, they have a 1 polarization. They don't have a 2 polarization. They have a 1. They had 2 initially, but Voyager kind of it malfunctioned and a polarization switch died. and that's why by skip and there's only transmission one polarization. So NASA always implements both polarization in any spacecraft that I've worked personally. They always have two sets of antennas, right hand, left hand on both sides of the spacecraft. They have 4 antennas. And this is important because the polarization could switch in because it's reflected at something. And that's why we can switch on the ground. So that's why I don't know which polarization actually, even though Voyager transmitting right-hand polarization, by the time it gets to us, it's going to be still right or it's going to be left switch. That's why I have it choose 2 independent switches. It'll tell me that I have a right way or I have a left way polarization. So basically each part of the feed going to pick up on direction. Sorry,
Yeah,
I'm just too far.
No, that's fine. That's what I was referring to in regards to the on reflection from your parabolic dish, the reversal of the polarization. So that's what I was referring to. So that when you select right-hand polarization, that's actually the signal that you're detecting, and not necessarily the reverse that would be received at your feet.
Yeah, exactly. Sorry, yeah, if I kind of misunderstood that, but we are receive system only, right? So I kind of start mentioning like transmit, receive, but we don't have none of that. So we have only receive. So not only we care what signal comes to the antenna. So at the time it comes right hand, it turns away and switches to left hand, and that's what the left hand portion will pick up. But I don't have simultaneous receive on both polarization, which I initially wanted to do diversity. So I want to have both, then mathematically calculate it and plot it, so I would never see like fades. But in this case, you know what? That's over too complicated in the system for no reason. I can always physically switch. If I'm detecting the signal, I can switch the polarization going from left hand to the right hand physically on my feed. It'll tell you which polarization the signal is going to be strongest. Based on the previous results that I had from other guys and the scientists that work with Voyagers, they normally receive on the right-hand polarization. So just having a right-hand polarization, the feed itself would be sufficient. But I want to go further and have capability for both.
Okay.
Any other questions?
Well, thank you very much, Alex. You've been great. This is what I call pure science.
Well, it is. It is pure science, and initially I didn't want to go that far. Okay, it was just a simple system, because it's a purely, it cost money, things like I want to do, but you need to get them, you're going to implement, and I'm like, okay, I'm going to switch amateur radio guy. This is the cheapest guy in the world, right? So we're trying to find everything cheaper. I'm a scientist guy, which my primary job as a senior scientist to do science, to do these numbers, to do these approaches, to do these configurations, and now do Python coding, which I do at work as well. I don't care how much it's gonna cost. I want to get the function. I want to get what the purpose is designed for. Otherwise, it won't justify all these hours that I spend. And so that's why, and I want to go further away, not just to do hardware stuff, but also trying to implement codes that will be helpful, not just for this, because I don't want to be guy Alex does everything just for his system, but it's also helpful for us because I'm part of DSES, right? So I don't have no limits at this point to design any hardware or any software capability whatsoever. Just tell me what do you want, it's all going to be done.
Great. Bill Miller, you got any comments?
Now, the question is going to be where we're going to implement that. So, because we have so many projects piling up, I want to make sure we have spare time allocated for all of that. Yeah. At my point, I'm at the conclusion of it. So I just want to work on that software, but that software does not impede anything.
Yeah, well, I'm glad we got this update because that helps us in terms of planning and moving forward with this. And September is going to be a busy month, and probably October as well. I know you're going on a DXpedition, I believe, in October as well. So we got a lot of balls in the air, so to speak. But we'll fit them in. We'll look at the calendar. I'll talk with Rick and Bill and the other guys, and see what the best timing is. Full moon is probably what you're looking for if you're going to be getting the noise off the moon. And the next full moon is September the 7th, which is
too early,
right?
Yeah, right after our
Yeah.
social event. So if
Towards
you
the-
want to come on down in September,
What?
come on
Yeah.
down for some burgers.
Well, unfortunately, I have to skip that. I'll be just coming back from my Honduras trip, which going to be followed. Well, I'm going to be in Japan in 2 weeks, and then coming back from Japan, going to go to Honduras, and then we have
We'll
all
talk
this
about
event.
that later. Then we
Right.
we can discuss that. And you can,
But I'll try to come at open house. That's going to perfect opportunity to do work with the EME Diane system.
yeah,
Um,
that's the Diane.
Right. So because we have a Diane question as well that needs to be kind of brought up here. And we'll postpone DSN. That's fine. We have more time for me to doing this and someone do the mechanical aspect for the feed amount.
Yeah.
And then I'll try to plan 17th, September 17th, you mentioned. Plan to come. I don't have trip booked yet, but I already booked trip for contest. Me and Vlad is also coming. And yeah, speaking on that, let me one more thing. Okay, I wanna. So we have another donation, and this time donation is the SDR receiver. This is commercial SDR receiver. It's a National Instrument receiver, SDR, but this is the actual B210. This is the first generation because it came from the National Instrument Device Laboratory and then adopted by Atos. So the Atos is actually this, but this is the first generation of commercial available SDR. So it received from 70 megahertz to 4.4 gigahertz. So it's been donated by W6BVB. So we can use this for any purposes. It has very good performance, way better than AirSpy. So we can utilize that. So I'll bring this on my next trip.
Sounds good. All right.
By the way, this is $2,500.
Thank you. Thank you. I appreciate it. And definitely gonna watch for him as well. And be great to see him again. All right, with all that said, thank you, Eric, for everybody who attended. And this is going to be recorded, and we can see if we can get this onto our YouTube page, and so that other members of our group can watch it again, because I think it's fascinating.